user might not experience like the user might feel like some delay is there in the receiver in the received data. So to overcome that, we are using this buffer mechanism. So this is how the receiver code has been designed. Is there any doubt in this? Hello.
No, Ajay, no.
Okay. If this is clear, I will show you how the transceiver works. So now this is a receiver front panel, and I will be taking out the transmitter front panel. So now I am transmitting at 200 kilo accurate and 1000 bits per packet. So I will run this code. Okay. So it's transmitting. So we can confirm that by seeing this constellation diagram, so that it's transmitting. And next, I will start the receiver as well. So initially, we can see there is no data inside. So after it starts receiving, it starts to decode. So this is how a constellation looks at receiver side, and the eye diagram, which is very good, and the equalized constellation. So if there is any bit error or some bits might have been missed out, the equalized constellation will make sure that it estimates the bit that has been missed. So this is how it looks. It's similar to that of a transmitter, and this is the equalized eye diagram and the IQ waveform. So as you can see, there is a gap in between this. So this is one packet. This is some another previous packet. So this is taken care by the packet passing at the receiver side, as I've shown before. This is the receive text. So now I will be showing. Okay, so if I change the data here, I will stop the transmitter and receiver. Okay. So now I will be transmitting at different IQ rate. So I will be giving 300 kilo. Here also 300 kilo. And at 1.2 gigahertz, I will be transmitting. And I will reduce the gain as well. Okay, so I've turned on the transmitter. It's transmitting. Now I will turn on the receiver as well. As you can see, there it's decoding the data. So I have given space as well, so it's properly decoded. Okay. Another thing we can change is so I'll be showing you by changing the text. So if I write but 1, 2, 3. The data changes there as well. Okay. So using this transreceiver code, we can easily develop. We can transmit audio, image, and PN sequence as well, so that we can determine some error is there or not. So this all can be done using this transreceiver code. Okay. Are you clear of this? So how this transreceiver code works?
Excuse me, sir.
Yes.
I have a small doubt, sir. Sir, when
Okay.
this in block diagram, when this packet switching will happen, sir? If you go to
Packets.
the block diagram.
Yes. So here you can see there is an VI called as RX pass packet. So here the packet passing happens, where it will wait for the previous packet to come, and if that previous packet is there, then only it will go to the state and it will start stitching the packets.
Okay.
So you can explore that inside this, how it's been designed.
Sir, during the decoding process, if some bits are lost, or I mean, say some chunk of data has been lost, as you said that after decoding, it will wait in the buffer for some time.
Yes. So
Doesn't it take more time if anything is lost or if we get any delay during this?
no. So for that, what we have done is there is an another state. So if it happens for more time,
Hmm.
we just pass it to the next state, decoding packet, so that there might be no delay in between the data that you see. So you can see there is a two states. So this happens when the proper packets are there.
Okay.
So this state is nothing but there is if there is one packet somewhere it's missing. So it gives out for the next state, and it will wait for the processing to happen, and it will retrieve that missed packet from there.
Okay. Thank you.
Okay, is there any question based on the SISO transceiver?
Yes, participants, if you have any questions, you can ask or you can either put them in the chat box. Yes, Ajay, I think we can proceed.
Okay, so this is all about SISO transceiver. Now we'll be going through the OFDM transceiver, how it works, how it's been built, what is the importance of it. Okay. Uh, Before that, shall we take a 5-minute break? Or else shall I continue the session?
If you really want to have a break, you can take, or else we can continue.
Yeah, it's if they want, I can give, or else
No,
I
no,
can.
no. It's okay. It's okay.
Okay, yeah. Okay, 1 minute. You can see my screen, right?
Yes, it's visible.
Yes, thank you. Okay, so now we will be going through OFDM, which is orthogonal frequency division multiplexing. So what are its importance and how it has been built, we will be going to that. So what is before going to the OFDM, I will tell you why it is required. So today, in one of the most exciting area in communication system field is wireless communication. So everybody wants their device to work at peak speed, and there is easier to achieve when there are few devices, right? In the last decade, wireless communication system has been one of the fastest growing technology in the world. Further, wireless communication system are expected to be reliably providing a data service with high data rate, that is in terms of megabits up to gigabits. So this challenge to ensure the fulfillment of this requirement arises from the limited availability of the frequency spectrum. So the total power and the nature of the wireless channel. So furthermore, in broadband applications, wireless communication encounters frequency selective fading, which leads to several intersymbol interference, both in time domain and frequency domain, impacting the service quality and data rates. So, to meet this need for high data rate and reliability in data service, multiple carrier modulation has been used. So, So the multiple carrier modulation is a technique for transmitting the data by sending data over the multiple carriers, which are normally closely spaced. So this multi-carrier modulation has several advantages, including resilience to interference, resilience to narrowband fading, and multi-path effects. So these are the many advantages that you can see in a multiple carrier modulation. So as a result, multiple carrier modulation techniques are used for data transmission, as it can provide an and effective signal waveform, which is spectrally efficient and resilient to real world environment. So this is a brief introduction about why multiple carrier modulation is used. So I'll be going through different modulation techniques right now. So as I told, the number of users increases. This accommodation, everything. Sorry. Thus, vital allocation efficiency. So to overcome this, we'll be using multiplexing schemes. So there are different multiplexing schemes. Like we can see here, the time domain multiplexing, frequency domain multiplexing is there, code division multiplexing is there. In time multiplexing, there is a time division multiplexing where the messages are sent at different time slots on the same channel. So there will be a single channel for example, there will be a single channel. Okay. Inside that, we will be sending the message in different time slots, like at T1, T0, T1, T2, we'll be sending the messages. In frequency division multiplexing, we will be sending the message at different frequencies with some God bands. Like God bands is nothing but the spacing between two carrier signals. And next is the OFDM, where the message is sent by overlapping each subcarriers one above the another. And then is the code division multiplexing. So here we transmit simultaneously using an unique codes. So these are the three multiplexing technique. I will be telling what are its advantages and disadvantages in further slide. So next, the setback of the multiplexing. So in time division multiplexing, we have to wait for their returns, like increasing the latencies. So if we see, the first data goes in like this, and it goes to the demultiplex. It is having only 4 slots. So until the 4 slots are free, the other 4 slots should wait for that to get freed. So if this is going first, this should get decoded first. After that, this will go in. So this will increase the latency, and it will increase. It will take more time for doing a transmission of the signal. So after that, the frequency division multiplexing. In frequency division multiplexing, as I told, we'll be adding an God band, which is the gap between two channels. What we are doing is we are using more of the spectrum, but our spectrum is very narrow, right? Like there is some set of frequency band that will be given for mobile communications, data communications, and all. So within that range only, we should be using the spectrum. So that is one disadvantage of frequency division multiplexing. So next is code division multiplexing. So the main disadvantage of that is it self-jamming happens, and it's like it decreases what we say accuracy when the more number of users are there. So to overcome all this, the best method is orthogonal frequency division multiplexing. So this orthogonal frequency division multiplexing, that is OFDM, is a promising multi-carrier modulation techniques that mitigates the effect of frequency selective fading inherent in high data rate environment. It is a type of multi-carrier modulation scheme based on the idea of dividing the given high bitrate data stream into several parallel low bitrate streams and modulating each streams on separate subcarriers, often called as which we call it as subcarriers. So each subcarrier is modulated with the conventional modulation schemes that can be QAM, PSK, or some modulation technique at low symbol rate. So this maintains total data rate. So this will maintain the total data similar to that of single carrier modulation scheme with same bandwidth. So the main advantage over this single carrier modulation is it has the ability to cope up with the channel conditions. For example, attenuation of high frequencies, narrowband interference, and selective fading, due to which caused due to multipaths and all. So we can see this. So this is if there is one signal and it has been divided into multiple subcarriers. So the subcarriers, you can see the red one is first subcarrier, second one is blue color, and another one is purple color. So this is how we can divide a single signal into multiple subcarriers so that we use the spectrum efficiently, and it is also orthogonal to each other. So we can see if we take at this time slot, there is no other signal interfering to this. If you take at this time, there's no other signal interfering to this. So there will be no signal overlapping each other. So there will be no intersymbol interference as of such. Okay. So this is about orthogonal frequency division multiplexing. Yeah. So the information modulated in discrete time. Each user has the different center frequency with the allotted bandwidth. So particular bandwidth will be given, and particular center frequency will be there. So if the carrier signal modulation system has T symbols, then it will take n subcarriers. So you can divide that T symbol into nt. Like you can divide the symbol into small chunks. So that's how the OFDM is built. Okay. So yeah. So this is how a uh, OFDM packet looks like. So first we'll be adding the training sequence, which is of two sets. I will tell the advantages of using this two training sequence at start, and then we'll be having a cyclic prefix, and then preamble. Preamble also I'll be telling in further slides, and then our data, OFDM data. So these training symbols we are using two copies so that the frame detection happens properly. So which in turn helps in correcting the phase and frequency offset of the data. So in orthogonal frequency division, the main problem that might cause is the frequency offset or phase offset. So this will be overcoming using an estimation technique, which I will be going through in further slides. So next is cyclic prefix. So training sequence we know. Next is cyclic prefix. So cyclic prefix is just a copy of symbols of OFDM message. So it helps in avoiding the interference between successive OFDM. It provides some period. It provides periodicity to the OFDM signal. So the linear conversion can be converted to circle conversion. So what it means is, so now we are having some OFDM symbol like this. So let's consider it as packet 1, and it is having some data at lump full. Okay. So what we do is we take a small chunk of data from backside and we append it at front. So this helps in avoiding the intersymbol interference, so that even though if the previous packet get interfered with this, so if I say that some other packet is coming in and it's interfering, other symbol is interfering with this symbol, so this can be very vital. Like we are losing some data here. So instead of sending only one packet at a time, what we do is we create a copy of that, so that we have the bit of information at last, even though the bit is corrupted at the beginning of the packet. So this is the use of cyclic prefix in OFDM. Next is the preamble. Preamble is nothing but a unique keyword that we give to the packets. For example, each of us will be having the unique phone numbers, right? So similar to that, we'll be giving an unique code word for each packet, so that the receiver can differentiate between the different users. So that is the use of preamble. So next is the transmitter, how it's been designed. So first the message data will be there, source coding we do, and channel coding, standard modulation, that is QPSK, BPSK thing, and the OFDM modulation. So in OFDM modulation, I will be going through what are there inside that. And then we packetize, upsample, pulse shape, and RF front end, that is USRP, will be transmitting it through. So as we can see, all are similar to that of SISO code. The only extra thing that has been added is OFDM modulation. Okay, so this an extra bit in OFDM. Next is inside, yeah. So this is how the OFDM block looks like. So first we'll be taking in the from the standard modulation thing, like after converting our bits into symbols, we will be making that symbols into a parallel manner. So after converting that symbols into parallel format, we insert key null tones. Null tones is nothing but the gold that we add in between two subcarriers, so that there will be orthogonality between each other. So if we are having a symbol like this, so there is some bit of null tones that will be adding in between each subcarriers, so that they do not overlap each other. And then we do is endpoint IFFT and insert cyclic prefix, and then parallel to series, and then we transmit through the USRP. Next is inserting null tones. So as I told, at the we'll be inserting it at the edge of the like starting at the end, and to avoid interference, as I told before. And this will be removed at the receiver side. So this and all I'll be going through in further slide. Okay. So IFFT. So why we do IFFT in orthogonal frequency division multiplexing? So initially what they were doing is we have divided the message into multiple sub packets, right? But it will be having different center frequencies. So to do that, it would have taken n number of multipliers and n number of signal generators. So you can see here, this is the traditional modulation orthogonality building technique. So there are different multipliers, n number of multipliers are there, along with n number of signal generators. And then we sum it up, and then we transmit through a channel. Again, at receiver side, we want to demodulate, we multiply it with the different signal generators, like different carrier frequencies, and then we take out the data. So instead of doing this, there is a technique called as IDFT, where the time domain signal is converted into frequency domain with different center frequency. So with change of n, like with change of k, different carrier signal as will be allotted. So instead of using n number of modulators, we can use a single regional signal processing technique to overcome this hardware compatibility. So that's why we use IFFT in orthogonal frequency division multiplexing. Next is the receiver. So in receiver, the passband signal will come in. That is RF front end is nothing but USRP. Match filtering happens, which is similar to that of SISO code, and simple timing recovery, downsampling, and OFDM demodulation, and again the standard demodulation, that is QPSK, BPSK, what we have selected. Symbol to bits mapping, convolutional decoding, and source decoding happens. So next is how the OFDM demodulation is designed. So similar to that of transmit in the SISO code, we do first symbol timing recovery, right? So in this symbol timing recovery works well, but there is a chance that the signals, the subcarriers that we receive, right, there might be a chance that they might overlap each other. And for example, like if the signal should be like this, instead of this, this carrier signal would have been moved something around left side. This happens because whenever we are working on with USRP, right? So there might be a chance that the local oscillator, which is inside USRP, instead of if we fix for 1 gigahertz, there might be a chance that it will give out 1.1 gigahertz instead of 1. Right? This 1.1 gigahertz, like 0.1 gigahertz change difference will impact more on the OFDM, because all are tightly packed, right? Even there is a small mismatch between the carrier signals, the decoding might not happen. So to overcome that, we do first frequency and frame synchronization, and then we extract the training sequence from that, so that we do channel estimation to overcome this ISI effect and retrieve the missed bits inside the packet. Then we do series to parallel conversion, which is opposite to that of OFDM modulation. Series to parallel conversion, endpoint FFT, frequency equalization we do, and then remove null tones and parallel to series conversion. So this is how the OFDM demodulation block works. So next is how this frequency and frame synchronization happens. So this is similar to that of transmitter, similar to the SISO frame synchronization, where we take a number of samples, and which is having the highest energy, we will take that as the sample rate, like sample. We will take that sample. So this is how it's been done in the OFDM as well. So next comes the Smith-Cox algorithm, where we will be estimating the frequency offset and the phase offset as well, because in OFDM transceiver, even as I told before, that even though if there is a small change in frequency, the subcarriers might overlap each other. So to overcome that, we'll be doing an estimation technique for estimation of frequency offset and all. So what we do first is we do a correlation with that of the training sequence. After that, we compute the average received signal power. So average signal power we will be taking out, and then we do an the like compute like R of D divided by P of D we get, and then we determine the M of D what we are getting from this. So after doing that, we will be taking out the phase of that. So by this we'll be getting the frequency offset, and by this we'll be getting out the phase offset that is happening at the receiver side. And so next is the FFT block that is in the receiver side. So as we are doing, as I told in traditional traditional OFDM, we are doing this modulation using different local oscillators, and then we transmit, and again we use different local oscillator. So similar to that, in receiver side, we'll be doing an FFT. Here we are doing the IFFT. There we'll be doing FFT. So here we'll be converting our frequency domain signal into time domain signal. So this, time domain signal to frequency domain. There we'll be doing a frequency domain signal to time domain signal conversion. So this is how the OFDM block works. Next is frequency equalization. This is very simple, nothing much as complicated as that of the transmit SISO receiver side. So here what we do is the receiver signal H of t is the unknown thing, and X of t is our transmitted signal. So we want only this. For this, what we do is we take the received signal, and we estimate H by doing just Y of F divided by H of F. In frequency domain, we just divide the received signal with that of the estimated H. So this is how the frequency equalization works in OFDM receiver. So I think have cleared the doubts of OFDM, how it's been built, how basic block works. Right? Is there any question on this?
Yes, participants, if you have any queries, you can put forth. Yes, Ajay, I think there are no questions. You can proceed.
Okay, so now I'll be showing the transmitter and receiver code, how it looks and how it's been built inside. Let me open the file. Yeah, you can see my screen, right?
Yes, Ajay, we can see.
Okay, yes, thank you. So this is how the project looks like for OFDM. Inside the OFDM packet transceiver, you can find the code of transmitter and receiver, and inside transmitter. Okay, so this is how OFDM front panel looks like. Similar to the SISO code, normally we'll be giving the SRP device name, IQ rate, carrier frequency, gain, antenna selection and all. And here the extra bit that we are doing is null tones, how much God bands you want to add to the packet. And then we can choose the FFT format, like if you want to do a 128 FFT or 256 512, depending upon the application, you can select. And then the cyclic prefix you want to add, you can select from this control button. And the PSK modulation technique. So here we can transmit 8 PSK, 16 PSK, BPSK. Depending upon the application, you can select. Okay. This conversion is similar to that of SISO code. And then the channel length, as I explained in SISO receiver code, it's similar to that of this. Okay. So you can see, if you want some reference of how it's been built, you can see the block diagram here. Okay. So we'll go through the transmitter block diagram, how it's been built. So first, what we are doing is we are, as it's an orthogonal signal, we are having 5 users. So these 5 users will be allotted different carrier frequencies, as I've mentioned before. So this is how. Sorry, 1 minute. Okay. Huh. Yes. So as you can see, there are 5 users here. User 1, user 2, user 3, user 4. So that we can see on block diagram as well. So user 1, we are building an array from that, and we are passing it to an assigning subcache. So this vi assign the subcache for each users, and then it goes to an for loop where the packet number gets added. So before the packet number gets added, we should be doing some OFDM modulation things, right? So for that, what we do first is we take the message bit of each user, we convert that into bits, and then we add a preamble. As I told before, we are adding a preamble so that each users will be having unique codes for them, so that the receiver can identify that each subcarriers are different users. So that you can see here. I will show you how it looks. Yeah, so these are the preambles that we have given. So these are the unique codes. As you can see, these are different from each other. So each user will be assigned a single code, that is unique code. So that goes through this, and this also will be converted to bits, and then we do convolutional encoding, and then convert symbols, convert bits to symbols, and then OFDM modulation happens here. So and these two blocks are similar to that of SISO code, and this is one extra that has been added here. So you can go inside and see. First, what we do is inserting null tones. So we have already divided the like assigned the subcarriers for each user. Now we will be adding a null tones for each carrier signal, so that they don't overlap each other. And then we do is IFFT, as I've told in the presentation, that we'll be doing IFFT, and then we add cyclic prefix. At last, we do series parallel to series conversion. So we do this parallel to series conversion because we can transmit the signal in serial format only, right? So that's why we do series parallel conversion, and then we add the packets for each. So here where the packet numbers get added to each frame, right? Next is same upsampling. Then we do pulse shaping, and then it as I've told, this is a state diagram. This goes to a transmit data. So first it will validate a similar to the of SISO code. Here it's now not been coded. We'll give an update of that. After it's been coded and it will be converted into waveform, this waveform will go through the USRP. So as you can see here, first we are opening a session of with USRP, and then we are transmitting, like dumping in the data what we have processed in previous loop. So here this we have dumps the data into the USRP. So as I told before, we will be using this inside a while loop, so that it keeps on dumping in the data uh, to the USRP. Okay. After that, at last we close the session. So this is how the transmitter block looks like. So we can see constellation diagram similar to that of SISO code, constellation diagram, I diagram, and IQ waveform. So this is how the transmitter has been built. Is there any question in this? Hello? Are there any questions?
Yes, participants, if you have any questions.
Excuse me, sir. Sir, can you once again explain this transmit data block, sir?
Yes. So what happens is it's an orthogonal frequency division multiplexing, right? Where we assign subcarriers for different users. So here you can see there are 5 users. Okay. After that, what we do is we assign each subcarrier to single user. Like first subcarrier will assign to user 1, second subcarrier will be assigned to user 2, and so on. After that, we go inside this for loop. Inside this for loop, what happens is first we have to convert the bits to like the string to data, string to bits, right? Because we cannot process data in string format. So what we do is we convert the text that has been entered in by the user in this block, and we add a preamble for each user. So what is a preamble is nothing but the unique code for each user. So for example, as I told before, you have mobile numbers, right? Each are unique for one person. So similar to that, what we do is we give unique code for each user. So this will be given to first user, second user, third user, and so on. Like that, we'll be giving the unique codes. Okay. Convolutional coding. So convolutional coding and all, I think Raghavendra would have explained better. So convolutional coding we do, and then we do bits to symbol conversion, and then the OFDM modulation happens. So this and all, it's similar. These two blocks are similar to the SISO code, right? So we do convolutional coding and then convert bits to symbol. The only extra thing that has been added to this is OFDM modulation, where inside the modulation, first we do is inserting the null tones. So after each subcarrier has been divided, there might be a chance that they overlap. So to overcome that, we'll be adding some null tones. That is nothing but zeros we'll be adding at beginning or the end of each subcarrier. And then we do inverse FFT. As I've told in the presentation that instead of using n signal generators and n multipliers, we can do an inverse FFT to allocate different subcarriers, right? So that's why we do an IFFT, and then we add a cyclic prefix so that other symbol don't overlap a previous symbol, so that the inter-symbol interference doesn't happen inside. And then this is a parallel to series converter. So we transmit a signal in series format. So that is done inside this. And then we do normally the packet generating the packets. So here we'll be adding the packet numbers and the other information like training sequence and all will be added in this VI. And next is the upsampling, which is same as that of the SISO code. And then is pulse shaping filter. So after the pulse shaping filter, the bits, the symbols that has been converted will be converted by this what bits to symbol converter. Here it will be converted from symbols to waveform, because the USRP will take only continuous signal as an input. So that's why we used a pulse shaping filter at last. Like, so that all the data after being processed is converted to a continuous signal. So that we dump inside the USRP using this TX data. So this loop is there. No, this will dump the data into the USRP, so that the processing happens parallelly and the transmitting also happens simultaneously at a time. So are you clear of it right now?